maintenance shops. You look at vehicle maintenance activity, again, the trench drains inside the vehicle maintenance shop usually will go to a treatment tank. Washdown areas, any kind of vehicle washing. And again, we do a lot of projects with UPS where they're washing their fleet of trucks to a car dealership. Again, a lot of different applications there. And then manufacturing, as I said, if there's petroleum hydrocarbons in their process, we're working on a project right now for Boeing, manufacturing facility, to secondary containment requirements. So again, if we're looking at containment of large oil spills or catastrophic releases like a transformer or some sort of a petroleum storage area, again, these products are used for that. So why are oil water separators and oil interceptors so important? So here we see a big 20,000 gallon underground oil water separator being installed in the Carolinas. And again, this is a Duke Energy facility. So this sizing for this product is not only peak gallon per minute flow rate. So we look at rainfall, we calculate surface area, what's the peak gallon per minute flow rate that this tank has to treat. We also look as another factor for sizing is the largest potential oil spill. So at this facility, we had a bank of transformers. The largest transformer holds 10,000 gallons of oil. If that ruptures, we might use this oil water separator to capture the largest spill, and we'll size it for that. Or maybe the transformer has a dike area around it that, for fire conditions, they want to evacuate that oil around the transformer. We have to have a tank or an oil water separator sized to capture that large flow. So here we have a video. This tanker truck driver basically has his hose hooked up to this underground tank. So he's fueling this underground tank. So this tanker truck, basically is fueling this. I'll just go ahead and start this video. And basically, the parking brake is not fully engaged. So the truck starts to roll. Thank God nobody was hurt. The driver ran in front of the truck. This hose rips out. All this petroleum, fuel is going onto the pavement, going down into the storm drains. He thinks he has the truck engaged, but it starts rolling again. He runs back and engages the brake again. So while that's happening, all this fuel is running on the pavement and into the potential drains and into the environment. So a lot of the projects we do, we're sizing for the worst potential spill like this on top of the large flow rates for stormwater or what have you. So tanker truck like this, usually we'll see maybe a 3,500 gallon as the biggest compartment of the tanker truck, to some custom applications like down in Miami Airport. We had a project last year where the tanker truck was 18,000 gallons of fuel. So these are things we look at when sizing and designing the product. So the fact of the matter is petroleum releases are very common. If you go out today in the Raleigh area to fuel up your vehicle at a gas station, you look down at the pavement, many times you'll see a rainbow sheen coming off of that pavement. So what that is just people spilling fuel on the ground. Small releases are very common to something like this, where the fire department's called in and you have, the EPA called and that type of thing, or the video with the tanker truck. So we have federal regulations from the EPA to prevent these oil spills from getting into the environment. You have your oil pollution regulations, which are your SPCC, spill prevention, control, and countermeasures, which are basically written plans designed by you folks, the engineers, for a site-specific facility or customer. And what drives a spill plan is oil storage capacities of 1,320 gallons or aggregate volume or more, and or the location of the facility might require a spill plan. So in that written spill plan, you might have an oil water separator, you might have a spill tank. Of course, you'll have secondary containment, maybe with dikes and spill control and valves and things like that. For the storm sewer drainage applications, discharge regulations, we have the NPDES, National Pollution Discharge Elimination Systems. Back in the 1970s, the EPA targeted industrial activity with SIC codes. So they went after transportation, power generation, manufacturing. And basically, they require non-detectable, or I should say, no oily sheen leaving those facilities into stormwater. And that equates to 15 part per million or better for effluent quality. So SPCC, NPDES, we want to get under that 15 part per million, no oily sheen leaving the industrial facility. Now, other regulations that impact design are sanitary sewer discharge regulations. These are very regional around the US. On average, though, we see about 100 to 150 part per million for oil and grease as a requirement. So when I start getting into products, you'll see the differences in effluent quality and how we meet these regulations. On average, 100, 150 part per million. There's exceptions to that. New York City, believe it or not, is 25 part per million, whereas Chicago's 250 part per million. So as a design engineer, it's very important we check for the authority having jurisdiction or the regulations for that sanitary sewer or stormwater for that matter. So now we move into products. We know what drives it. Federal regulations trickle down to state and local. So we have different products to satisfy the different regulations. So here we see the difference between an oil interceptor and an oil-water separator. The drawing on the left shows you an oil sand interceptor. It's basically a tank that has a series of baffles or compartments. And based on residence time, it's going to allow oil to float, solids to sink, and the discharge is going to be about 100 part per million for oil and grease leaving this tank. So this is very typical setup we see going to a sanitary sewer. Now this could be made out of our steel products. It could be made out of concrete, plastic, fiberglass. We see all of the above for different types of projects. The oil-water separator drawing on the right is a very typical product there. We're flowing from left to right. We have a series of inclined plates or coalescers, and there we're going to target a defined oil droplet size of 20 microns. We know mathematically if we remove that in the waste stream, your effluent quality is going to be about 10 part per million, and we're going to come underneath those stormwater oil sheen regulations. So you have two products here. Let's look at the first. Oil sand interceptors, as I said, they can come in different material of construction. They can go cylindrical, rectangular. The picture on the left is a cylindrical triple basin oil interceptor. That's being installed for a vehicle maintenance shop. And again, the key is we're going to discharge out of that tank to acceptable levels for a sanitary sewer. The picture on the right is a rectangular oil interceptor. Those are nice. We can get into smaller flows from 5 gallons a minute all the way up to 500 gallons a minute. So you look at the internals of this thing. Again, we're flowing from left to right. The contractor installs this below grade typically. So we're going to gravity flow in and out. The flow is coming through the left side there in the picture on the inlet. And the tank is full of clean water on startup. So when the contractor installs this, they'll fill it up with clean water. The fluid level will level off to the bottom of the outlet pipe. So that's going to equalize, that'll be your operating static operating level in the tank. We're flowing from left to right. As the oily water comes in, we have this diffusion baffle. Now this baffle does a couple things. The half baffle isolates the inlet flow, so you can get turbulence or surges coming into that tank. And the idea is we don't want to remix the oil and water that's already separated on the right side of that half baffle. Now we also have a 45-degree plate welded that basically acts as a velocity head diffusion baffle. As the flow comes in, it settles down the velocity, creating a nice laminar flow. It dissipates the flow to the full width of the tank, and it also diverts the flow to the head of the tank. So we want to start at the very front and use that full residence time to allow sand and solids to sink where we have a sludge baffle, and then oil to float on top of the water in that first compartment and get trapped in that compartment. Now the transfer pipe is taking clean water and moving it from compartment to compartment. So as we do that, we're basically knocking out the floating material, sinking material, and then discharging in about 100 part per million. So this tank can be set up for 350 gallons, rated for 0 to 35 gallons a minute, all the way up to a big 60,000. So we see these for vehicle maintenance, manufacturing plants, even parking garages. to something like this, which is a smaller profile, rectangular in shape. Same type of internals. Based on residence time, we're going to trap the oil and solids and discharge at about 100 part per million. So we've used these for enterprise car rental and manufacturing plants and different applications. The key is discharge to a sanitary sewer. They're going to take the wastewater and treat it at the wastewater treatment plant before discharge. Now, rectangular is nice because we can widen the footprint in that design and offer an oil skimmer pipe that's adjustable. So as that oil floats on top of the water, it skims off into a side oil compartment. So different options for design options there for you. We're also seeing these products on the oil interceptors used for hydraulic elevator pit applications. And I realize that's more on the plumbing engineering side, but again, we're designing a large medical center down the panhandle of Florida that has 14 hydraulic elevator pit sumps that we have to treat. So instead of going with multiple smaller interceptors like this, we might have a common larger interceptor outside the building below grade. And of course, the elevator pit would have a sump. We've got a sump pump that has a sensor. This will pump automatically to the above ground oil interceptor, or as I said, maybe a larger one outside the building underground. We size these elevator sump pump applications according to ASME A17.1 standards, which requires 50 GPM per hydraulic elevator. So again, that if you have one building with one elevator, we would go with 150 GPM interceptor. If you got 4, we would go with one 200 GPM or multiple 50s to take each drainage point. As I said, that 14 hydraulic elevator pit application for the panhandle, for the big medical center, we might take a larger interceptor outside the building and take all those drainage points to one large tank. International Plumbing Code 2015 basically requires the elevator pump not shut off in emergency conditions for firefighters. That's why we need an interceptor for that application. So even if the pit is full of oil, we want to be able to have an interceptor to collect and trap that oil so it's not discharging into the environment or into the sewer system. The oil-water separators. So again, we look at more on the civil side. This is a picture on the left is at O'Hare Airport. So if you can imagine O'Hare with the large surface area, rainfall calculations, this is one of many oil-water separators on the left being installed. The picture on the right is for an aggregate company that we work with nationally. So that's an above ground cylindrical oil-water separator. We're collecting the wastewater from the fueling operations where they fuel their vehicles, and we're pumping automatically to this above ground oil-water separator. When you look at the inside of this tank, again, we're flowing from left to right, tanks full of clean water. Again, as that flow comes in, that diffusion baffle is going to do its job. It's the same as we use on our oil interceptor. So that's going to isolate turbulence, direct the flow to the front of the tank. The yellow droplets that come in represent oil. So the big droplets are going to float quickly in the water. The smaller ones move through the inclined plates. Now that inclined plate system is angled upwards at about 25 degrees. The corrugations on the bottom will trap the oil, forcing it to collide and coalesce and form larger droplets of oil. So that oil is being driven upwards. The black represents sand and grit. As that comes in, it hits the flat top and slides down to the bottom of the sludge baffle there. So you can see oil's building on top of the water, solids on the bottom there. We have a secondary coalescer that is an oleophilic oil attracting mesh material that's attracting small oil droplets down to 20 microns on the petroscreen that's coalescing and rising to the top of the tank. As oil builds up, we've got this float, stainless steel float system. Those are weighted to float in water and sink in oil. So as oil builds up, it's going to sink the top float first, sound an alarm on the control panel. Vac truck will come, drop a suction hose down that pipe, that 4-inch pump out pipe next to the floats, and pump the oil off the top of the water. And then the customer fills it back up with clean water and they're ready to go for another cycle. So clean water's flowing out through the downcomer pipe on the right side there. So as we flow through this vessel, we're going to size this for about a 10-minute retention time. So it's going to take about 10 minutes to flow through this vessel and separate the oil from water. So we look at some highlights to this. And again, Highland offers one design on this. There's other units out there that offer different types of coalescers. The key is the effluent quality here. We really like this velocity head diffusion baffle. We use it even in our passive grease interceptors because it works so well along with the oil interceptor and oil water separator products. The plate design that we use is called a Corella plate. It's a combination of corrugated and lamella. So lamella is a flat plate that does a really good job at settling solids as they settle on the flat top of the plate. That's angled upwards, so the solids would slide off and be directed to the sludge baffle. The corrugated bottom basically is the corrugated plate, and that's going to trap oil as it's floating. It's going to trap it, force it to collide and coalesce. And the idea is that oil droplet is getting larger and more buoyant. It's going to rise faster in water and float to the top of the water there. So that Corella plate is a combination of two plates. The Petroscreen is an oleophilic polypropylene mesh material. It's bundled in coated steel cartridges, which can be removed through the manway, and that's going to target the small droplets of oil. And then your downcomer pipe. So that downcomer pipe set at about 20% off the bottom of the tank. We can fill oil, float oil on top of that water and trap it and take clean water from the bottom of that vessel. So again, looking at the inside of these things, you saw rectangular, cylindrical shapes. This picture on the top left is your downcomer pipe. So that's heavy duty steel construction. It's blasted and coated. You can see it's set at about 20% off the bottom of the tank. This rectangular frame is the secondary coalescer. So the coalescers will drop into this frame. You can see we weld baffles around the sides of this frame in a cylindrical design. So all the wastewater has to go through that coalescer. So the picture on the bottom left there is the Petroscreens or secondary coalescers. They drop down into that frame. And then the picture on the right there is your Corella incline plate. So that's going to do its job and take out the heavy oils. And then the Petroscreen secondary coalescer is going to take out the small droplets. And again, at the bottom of that plate face, that corrugated plate on the right, you've got the sludge baffle. So that's going to collect sludge and dirt, or sand, I should say, as it sinks in the waste stream. So as engineers, let's look at design, selection and design. When you look at designing these products, and again, it doesn't have to be Highland, but good idea to make sure your inlet run piping is straight as possible going to the oil water separator or interceptor. Again, we want to alleviate any 90-degree turns or elbows in the pipe that can create turbulence. So you want to try to keep your pipe runs as straight as possible. If you have to pump into an oil water separator or an oil interceptor, you want to make sure you specify low shearing positive displacement pumps. We want to try to avoid the risk of a mechanical emulsion. If you have to pump, positive displacement, low shear pumps on the inlet. If we're going on the outlet side, we do submersible pumps all the time, centrifugal pumps that actually pump clean water out of the tank. We don't have to worry about mixing the oil and water. Too high a feed rate. So we want to make sure we're sizing these products for the peak worst case flow rate. If it's undersized, you could see backup, everything upstream backing up. You could also see, for a large flow, the tank's not rated for, it could actually push oil up into the manways, push oil out of the tank. And then detergents. We want to make sure that if the customer's doing any cleaning surfaces or vehicles, we want to make sure they're using quick releasing biodegradable detergent. We call that oil water separator friendly detergents. There's a lot on the market versus a chemical emulsion that will impede the separation process in the tank. Inefficient oil removal, sludge buildup. Again, we probably move about 600 systems of these a year, and we get about 3 or 4 phone calls. Hey, the oil water separator is not working or interceptor is not working. First question is, when's the last time you cleaned it? So again, they're not magical boxes. They have to be cleaned out. We recommend once a year as rule of thumb, and that would take care of sludge, oil buildup, things like that. Freeze protection, again, for underground, for colder climates, we're burying these under the frost line. If we're above ground, we can, as a manufacturer, design heating systems in the tank, insulation for freeze protection, or we can bring the above ground into a heated building. When you look at sizing, so for outdoor or stormwater runoff, we take the area square footage you're draining from times rainfall, and that's inches of rain. On our website, highlandtank.com, if you look, we have a rainfall chart, a 10-year historical worst case rainfall, 1 hour rainfall in inches. So you just pick the inches of rain on that map. And then if, you can actually go to our website, type in the square footage, pick the rainfall, and we have a calculator there to do it for you. But if you want to do the equation, you take area square footage times inches of rain times 0.0104. And that'll give you a peak gallon per minute flow rate. For indoor applications, we follow the International Plumbing Code, and that is just taking square footage. Again, we have a calculator on our website, but you can times it by 0.00748, and that'll give you a gallon per minute peak flow or size oil water separator. The other things to watch out for when sizing is largest potential oil spill. And usually that'll be the bigger factor when we look at sizing here. For design, a couple design things to think about. Vessel volume. So as I said, we size for about a 10-minute retention time. So our flow is 1/10 the volume. So if you look at a 10,000 gallon oil water separator or oil interceptor, that's going to be rated for 0 to 1,000 GPM peak flow. A 1,000 gallon volume unit will be rated for 0 to 100 gallons a minute. So 10-minute retention time is pretty standard for us on our designs, but we do see some Army Corps of Engineers and military requirements for a 30-minute retention time. We can certainly accommodate that with bigger tankage. You just have to let us know what you're designing for. Reducing volume, we feel, is a bad idea. When you make the tank smaller, you're going to lose oil storage capacity, sand storage, and again, more frequent maintenance will be required with a smaller tank as well. Another design issue or thing to think about is API. So in the American Petroleum Institute manual number 421, there's a calculation there based on Stokes' law. And we size our incline plate, the Corella plates, the petroscreen surface area according to this equation. So we can actually give you the square footage required for the size oil droplet, specific gravity of oil that we're removing from the waste stream. So again, API 421. The incline plates. The incline plate technology has been around for 50 years, listed in the API manual. But again, as a manufacturer, we've taken that and enhanced it, by providing 2 plates in one called the Corella. We've got the lamella and the corrugated. But a plate design basically shortens the vertical distance an oil droplet has to travel. So that's going to, trap that oil, force it to start to coalesce and collide and create a bigger droplet of oil. And obviously, the bigger the droplet, the faster the rise rate in the water. UL 2215. So UL 2215 is a standard. As a manufacturer, we're one of 30 oil water separators that have been tested and can carry a UL 2215 label for our oil water separator. So from an engineering standpoint, it gives you, the specifier, a comfort knowing that the design has been tested. It's been, our effluent quality has been certified by UL, the performance, the construction, So again, something to think about for third-party performance label in the specification. UL 58. So again, if we're going underground, especially, UL 58, covers structural calculations. So we're dealing with maybe deep burial depths with long pipe runs, gravity flowing to the tank. You might be dealing with aircraft loading or military vehicles driving over the top of the tank. We can do structural calculations under UL 58 called a Rourke calculation. And that basically tells us how thick this steel has to be. Do we need to reinforce that tank based on these load calculations? And we can give you that specification and calculation. Lastly, access into the product. We want to make sure we have manways over critical areas so the customer can inspect and do maintenance on these products long term. Again, they're not magical boxes. They have to be cleaned out periodically, so access is critical. So if you look at this project here, this is an oil-water separator. We have large rectangular, we call these easy access manways. So when this unit gets buried, the coalescer boxes can be pulled out through the manway, serviced, power washed, cleaned. The tank can be vacked out with a vac truck, and then they can put the coalescers back into the tank. So easy access manways. If you're into waste streams that you're expecting a lot of sand and grit, we can lengthen our standard oil water separator and put a series G, which is a grit chamber, on the inlet. So we're flowing in through the left there. We have an additional grit chamber that's going to knock out sand and dirt before we flow into the main oil water separator here. And of course, we put another manway above that compartment so the customer can access that and pump out any sand or dirt that accumulates. We're using this for a project in Hawaii right now for the Hawaii DOT, where the harbor is taking containers from ships and offloading them. And there's a lot of sand and rubber and a lot of solids. So we have two 60,000 gallon G series oil water separators. So the G chamber is going to knock out the heavy solids and material before we go into the coalescing area. The Series J, so that's basically just including a lift station or clear well with pumps on the back end of the oil water separator. So if we can gravity flow to the oil water separator on the inlet, but let's say your pipe run, you're down pretty deep and we don't meet up with the effluent elevation to gravity out, instead of having you design a lift station downstream, we can just lengthen our tank, add a clear well with submersible pumps and floats to automatically kick those pumps on and off. So very nice design there. So again, a couple of project profiles, just kind of wrapping up here. With the power utility, we do a lot of work with Duke Energy in the area. Again, usually large oil water separators at the end of the pipe of the property. As a last resort, taking out hydrocarbons before discharge. We got a project with Alabama Power right now where they have a facility taking transformers from around the state and bringing them into this facility for servicing. Florida Power and Light, again, different customers in the Southeast there. Car dealerships. So Hendrick Automotive Group, those car dealerships have about 20 to 25 Highland oil interceptors, oil water separators, depending on the discharge. Military. So this is Jacksonville Naval Air Station in Florida. So this is a 10,000 gallon G series separator being installed. So they're doing fueling and vehicle maintenance for Navy aircraft and equipment. And again, it's the same premise. We're sizing for stormwater, we're sizing for fueling, potential spills, to a large stormwater project like this. So this was up in Canada a couple of years ago. This was a big manufacturing plant with Rio Tinto. And basically they had an oil discharge into the river. And the Canadian equivalent of the EPA, fined them and required them to upgrade their stormwater treatment system. So we went up, we did the presentation, we helped them design these 5 60,000 gallon oil water separators. So what's happening here is we designed for a peak flow of 25,000 gallons a minute. So that's all coming into an underground concrete detention tank. And then we're branching off into each of these 60,000s at equal flow. So again, very, very large stormwater project there. We can take all this and go above ground in cylindrical or rectangular shapes. The internals are pretty much the same as I talked about with an oil water separator or an oil interceptor. This was a project we did in Craney Island, Virginia for the Navy. So here we're taking bilge and ballast water from Navy ships, and we're expecting a lot of sand and grit and sludge. We designed this sludge hopper to run the full length of the bottom of the tank. We've got valves here where we can clean out that hopper. The engineer wanted to have access to the top of this tank, so we have a ladder, we've got handrails, and we specified large rectangular hatches, spring-loaded hatches that one person can open up a large hatch very easily for inspection and clean out. This was an interesting project we did in Lower Manhattan in New York City. So this was a Con Edison facility, and you can imagine after 9/11, all the destruction and cleaning up and new construction. Well, this 20,000 gallon above ground Highland Oil-Water Separators being installed 3 stories below street level. If you notice, it's white in color, so it's actually an above ground installation. The tank's on saddles, the tank's being lowered below grade into a concrete vault. So it's an above ground installation below grade. There's no backfill on the tank. And basically we're piping up to a containment area where we have a bank of transformers. So the largest transformer holds 10,000 gallons of oil. If that ruptures, this oil water separator is primarily there to satisfy an SPCC plan. So we're going to capture the oil in the oil water separator. And because we're down so deep in elevation, we have a Series J with a lift station. So there's a clear well on the back end of this tank with submersible pumps. We have controls that automatically pump the clean water out to meet up with the discharge line. There's that manufacturing plan I talked about for an indoor application. So again, rectangular, a little bit different shape. We're taking sump collection areas where we have wastewater from manufacturing processes, where we have cutting oils, lube oils, and we're pumping into that above ground separator. We also have a suction pump on the outlet. So we're pumping clean water from the outlet side as well. Here we have a duplex influent pump system. So that's tying into a sump. So again, this is very nice for retrofitting existing facilities. If you have a concrete sump that's in good shape, we can retrofit a new oil water separator with, this is showing duplex influent pumps there. If you're doing new construction and you want us to help design a influent collection sump, we can do that out of coated carbon steel or stainless steel. This is showing an influent sump tying into the underground piping. So that wastewater is going to gravity flow into the sump. We've got a series of baffles that will offer pre-treatment, knock out sand and grit, oil, and then the influent pump is going to kick on. We can do an air operated or electric diaphragm pump, and we pump into the above ground oil water separator there. I mentioned in the beginning of the presentation, you might see the need for secondary filtration systems on some of these products. And where that would come into play is either regulations going to drive that. We just did a project out in Wisconsin for a power facility where the local regulator required non-detectable levels of hydrocarbon coming off of that power facility. So now we go beyond an oil water separator. The separator is going to do its job. It's going to take out the heavy oil and dirt. There, we're going to go pump into a filtration system. That filtration could be a polymer filter. That could be an activated carbon or clay. It's going to adsorb the hydrocarbons down to parts per billion. So this could drive this by a strict discharge requirement. Maybe the client has oils that are very close in specific gravity to water. Maybe there's emulsions, maybe there's oil encapsulated metals, something in the waste stream that will give a coalescing unit a problem. We might see the need for a carbon or a filtration system there. So again, these are all made to order, as you can imagine. We would need a list of contaminants we're trying to take out. We would design, build, and test something like this. This is a skid-mounted filtration system. We've got the influent pump taking from an oil water separator from the clear well, pumping through bag filters to take out any suspended solids, and then maybe through these polymer filters, or we can get into some different types of media depending on what we're trying to accomplish. This was a Delta Airlines facility in Memphis, Tennessee. So here we're taking fueling and dike drainage. We're going into a collection area, pumping to this above ground oil water separator, and then from there going through the filtration system down to parts per billion. This was a project we did in at a regional airport in New York, Long Island, New York, in Suffolk County, Long Island. And basically this airport, MacArthur Airport, Southwest Airlines came in, operations were going great, so they needed to expand their fuel farm. So there you see 6 50,000-gallon above ground jet fuel tanks. We provided those with the catwalks, ladders. Those are single wall tanks installed in a concrete dike. So if you look at the concrete dike, that's going to collect rainwater, but we're more interested for this talk on the wastewater treatment system. So this is the drawing of the system. Basically, there's your 650,000s in the dike. So that dike area has a valve, so somebody can inspect the rainwater, make sure there's not a large oil spill. Open up that valve, the wastewater drains into the purple pipe. That purple pipe is sloped down to a concrete sump. Now you also have loading areas here. You've got a tanker truck on the right going to the fuel farm and loading the fuel farm with jet fuel. On the left there, you've got refueler trucks pulling fuel off the tank farm and refueling aircrafts. So both of those drainage points are going to the purple pipe and then into this concrete sump. From the concrete sump, again, most jurisdictions around the US, if you went through an oil water separator, above ground or underground, we'd get down to a 10 part per million. It would meet the stormwater discharges. But because this location of this regional airport in Suffolk County was on top of an underground water aquifer, the regulations or authority having jurisdiction was the Suffolk County Health Department. And they required non-detectable levels of hydrocarbons coming off this fuel farm. So this is probably the strictest you'll see around the country. Basically, from the oil water separator, we designed the filtration system. You've got influent pump, you've got a bag filter. We use these 40-inch polymer filters, and then we have these blue canisters filled with activated carbon. So from there, we're going to go to a holding tank. There's going to be sampling and record keeping done before they can discharge that water. So again, that's the strictest you'll see. So just wrapping up here, again, everything that we build in our 8 factories, we can ship on our own fleet of trucks. Everything's US manufacturing. The company's been around for 75 years. And again, if you have a project where you need to certify US steel, we can also do that as well on the projects. So with that said, just want to open it up to questions. Nobody really asked anything during the presentation, but maybe somebody has a question now.
Hey, Tom, it's Chaz. Thank you for that. Appreciate it. Excellent. I have a question as it relates to stormwater, being a stormwater guy. Have you guys considered green stormwater infrastructure? Because that's a growing trend with municipalities these days.
I'm sorry, what was the question, Chaz? I missed the first part.
Has there been any consideration given to green stormwater infrastructure for your projects as it relates to a stormwater side?
You mean as far as recycling stormwater?
Yeah, volume control and filtration, that sort of thing.
Absolutely. Yeah, we do have a whole division allocated towards that, which is another talk. But yes, we are doing stormwater detention, reuse for non-potable uses like flushing toilets, irrigation, condensate systems. But yes, absolutely. And that's more geared towards TSS removal and non-industrial discharges.
Yeah. Thank you.
Yes, sir.
So anybody else have any other questions? Feel free to put them in the chat.